Hey everybody, hope you're doing well. So today we're going to go ahead and take a really quick overview of Newton's laws and then really focus most of our time on applications of Newton's first law. We'll do an applications video for each of the three laws that Newton addresses, and we'll talk a little bit about how they work. We can also go ahead and we'll do a little more in class talking about how this applies to rockets, and we'll kind of go from there. Okay? All right, so let's go ahead and jump right into our essential questions. Number one, what are the simplified names for Newton's three laws of motion? They're common names that most people know the laws by, and this is a quick way to reference them when we're discussing them in class so that we know what it is we're talking about. Number two, what is inertia? This is going to be an important vocabulary word to make sure you know. So, what is inertia and how does it relate to mass? Number three, can you clarify the biggest misconception that many people have with respect to Newton's first law? We'll talk about what that is at the end of the presentation today, and then hopefully you'll be able to eloquently put into words why this is incorrect and what actually happens in these cases. Before we go ahead and jump into the laws themselves, I think it's worth going ahead and looking at who Sir Isaac Newton was himself. So let's go ahead and take a look at the man behind the three laws, and then we'll go ahead and look at the laws themselves. Excuse me. So Isaac Newton was born prematurely and barely survived on Christmas Day in 1642, which is interesting because that's the same year that Galileo died. And he definitely looks at Galileo as one of the people that influenced him in terms of his development of physical laws. He attended the University of Cambridge, but it wasn't until he was 42 that he began to write the Principia Mathematica Philosophiae Naturalis. So I guess there's hope for me yet, right? I'm right about the same age. Maybe my great breakthrough will happen soon. Then Newton showed that the universe ran according to natural laws, a knowledge that ushered in the age of reasoning. This is largely based on the publication of his work, Principia. All right. Inside Principia, the three big things that he wants to highlight for us that we're going to go ahead and focus on as we enter into the second half of our mechanics conversations are his three laws. So the three laws are obviously named after him and provide the basis for the study of dynamics and the fundamental laws of motion. We'll talk about them as Newton's first, Newton's second, and Newton's third law, but these are the other names for them, and you may want to use these because it'll be easier to reference than remembering which one's first, which one's second, which one's third. So the first law, the one we're going to focus on today, is Newton's law of inertia. Again, in order for this to make sense to you, you really need to know what that vocabulary word inertia means and how that helps to explain how things move or don't move. The second law is really the mathematical application of Newton's three laws, F equals ma, where F is a force, m is a mass, and a is an acceleration. We've actually already taken a quick look at this when we were looking at the concept of weight. Weight equals mass times gravity. Remember, gravity is the acceleration, and so weight is a force. This is an application of Newton's second law. And then the third one is the law of opposing forces. You hear this equal and opposite is a common term. They even use it in commercials and stuff today. But we'll talk a little bit more about how that's accurate and not accurate when we go ahead and get to our applications of Newton's third law. All right. So, if we were to summarize these three laws in terms of mathematical expressions, which is a lot of what physics does, this is what they would look like. In the first law, if the sum of all forces equals zero, then A, or the acceleration, has to equal zero, and the velocity will be constant. Whether that velocity is not moving, stationary, or moving, it's going to continue to move in that same direction at that same speed unless it gets acted upon by an outside force. Two, the second law is that the sum of all forces equals the mass times any acceleration. This works again because above acceleration velocity and here acceleration are vector quantities. And so this concept of direction is important when we start looking at forces. And then Newton's third law says the force of A on B is equal to the opposite of the force of B on A. Forces come in pairs. and the force from one on the other is the same as the one from the other on that force. Okay, so when you go ahead and push on a wall, it may not feel like a whole lot's happening, but as you push on that wall, the wall is pushing back on you. All right, this is the idea behind Newton's third law, and we'll talk more about this when we get to those applications. All right, so I think that's a pretty good overview. Let's go ahead and start taking a look more specifically at Newton's first law, the actual verbiage of it, and then how we go ahead and look at its implications in terms of what we're talking about in physics. Let's start out with describing Newton's first law. According to Newton's first law, an object at rest will remain at rest unless acted on by an unbalanced force. Unbalanced, so not at equilibrium. Keep that in mind with respect to what we talked about last class. An object in motion continues in motion with the same speed and in the same direction unless acted upon by an unbalanced force. Again, you're getting to this idea of an unbalanced force. All things being balanced, the object is going to want to maintain whatever state of motion it's in. If it's not moving, it wants to stay not moving. If it's moving, it wants to stay moving in the same direction at the same speed. This is often called the law of inertia. And so we need to understand what inertia means if we're going to understand why this is called the law of inertia. So, in its simplest form, this means that there is a natural tendency of objects to keep doing whatever it is they're doing. All objects are going to resist changes in their state of motion. In the absence of an unbalanced force, an object in motion will maintain this state of motion. All right. So you also want to realize that this is not a new concept. While Newton gets a lot of credit for his three laws, and rightfully so, this first of the three laws actually is derived from the work of Galileo, and he did some work on this before Newton's time. So, Newton's law of motion essentially states that every object continues in a state of rest or in a state of motion in a straight line at a constant speed unless it's compelled to change that state by forces acting upon it. We recognize this essentially as Galileo's concept of what inertia is, and that's why this is often called the idea or the law of inertia. So, what does that look like? Well, if we were to go ahead and neglect friction in its normal form, and we were to go ahead and use what this example you see here. If we drop a ball, it's going to roll down into the bowl and come back up the other side, and it's going to keep doing this forever because the gravitational force acting upon it is going to push it down. And so it'll get to a point where there's zero upward velocity and it will go back down and it'll keep going up and back and up and back. And that this position would be constant despite any changes in the steepness of the walls of the bowl. However, if we were to remove one of the walls of the bowl completely, what would that look like? Well, if you think about it, we have this initial position where we drop the object, the ball in this case, and it begins to roll down the hill. When it hits the bottom, it's going to keep going with that speed, and it won't stop until another force acts on it. Now, you may tell me that the ball always stops. Well, why is that? The force of friction actually decreases the rate at which the ball is moving, right? But without that, the ball would just keep going forever. Now, you probably understand the basics of this from middle school or your freshman physical science class, but you might be a little surprised to learn that Newton really wasn't the genius behind this. Newton himself wrote that he was only able to understand as much as he did because he stood on the shoulders of giants, and Galileo was one of these such individuals. And see far he did. Although the law of inertia identifies forces as the actions required to stop or start motion, it didn't quantify those forces. And we're going to rely on Newton's second law next class to go ahead and do the mathematics to go ahead and quantify these. So let's set out to go ahead and define inertia so that we have a good idea when I say it, when you say it, what it is we actually mean. Inertia, then, is the tendency of an object to resist changes in their state of motion. Newton's conception of inertia stood in direct opposition, however, to the more popular conceptions about motion. Everybody thought that it was the natural tendency of objects to stop, and that you had to keep applying forces to them to keep them going. And you can see how they would think this because of Earth. Now, on our planet, we have gravitation, which creates friction, and so the natural tendency of objects is to stop moving because of the friction forces. But this was not true in Newton's time. It was believed that moving objects would eventually always come to a rest, and that any object at rest would stay at rest. And this dominated people's thinking for about 2,000 years. So, this is one of the places where we start looking at the scientific process, where evidence is so crucial to go ahead and draw people away from the normal routines and understandings that they have with respect to things like inertia. People thought everything wants to stop till Newton comes along and says, no, nothing wants to stop. They want to stay the way in the form that they are, but if they're moving, they want to stay moving, okay? Unless it's acted upon by an unbalanced force. So, how do we measure this concept of inertia? Well, the simplest way that we really look at this is by using mass. All objects are going to resist changes in their state of motion, according to Newton's first law. But some objects are going to actually have more of a tendency to resist those changes. And the tendency of an object to resist change in its state of motion varies with its mass. Mass is the quantity that is solely dependent upon the inertia of an object. The more inertia an object has, the more mass it has. The more massive an object is, the greater tendency it has to resist changes in its state of motion. Now, I actually, weird little thought, but I always remember my high school days reading the old Spider-Man comic books. There was a character named the Blob, and one of his big things was he was so massive that he almost had his own gravitational, but that he was immovable. That's what I think of when I think of inertia, is that he was so massive that his inertia was really high and he was really hard to go ahead and move. Now, there are plenty of examples of this, and I know I always have a tendency to make sports examples out of them, but there are lots of them. If you slide a hockey puck on ice, it eventually stops. Why? Because of the friction of the ice. It will also stop if it hits something like a player's stick or a goalpost. This is a great example of Newton's first law. It stops or changes direction because of an unbalanced force. If you didn't, it would just keep going. And in fact, if the ice was a little bit melted and there was limited fluid friction, it could keep going for quite some time. All right. But ultimately, there is a force, however small that force of friction may be, and the object stops. If you were in outer space, let's say you're just off the moon, you're doing a little work on the outside of a space station, and you kick a ball, soccer ball, something like that, it would keep going forever. Um, when we say because there is no gravity, there's no heavy gravity. Yeah, there's always gravity. Gravity is an infinite force, like we talked about before. But the direct impact of really strong gravity, if you're in deep space, is minimal. It's what they would call microgravity. And because there's so little material in space proper, there's little to no friction, there's almost no air resistance going against it, and the ball just keeps going. It only stops going in one direction if it hits something like a meteorite or it interacts with a heavy gravitational field of another planet or a black hole or something like that. Another example of what we're talking about is if you're driving in your car at a very high speed and you hit something. So, one of the things we can start looking at is collisions, and we'll get more into this later on as we go through the course. But what if you're driving along and you hit a brick wall or you run into a tree? Well, the car comes to an almost instant stop, but your body has a tendency to keep moving forward. And this is why cars have been engaged with airbags and seat belts is to protect you from smashing into the windscreen, the windshield. Right? Now, I have a little video for you to go ahead and show you the amount of change in force in terms of unbalanced forces when you deal with a car crash. So, if you're a squeamish person, um, watch at your own peril. You don't actually get to see any humans or anybody get hurt in this, but you do definitely see the point of collision. All right. So we're driving along on the afternoon, obviously not in the United States. So you can see the characters on the ground and the fact that you're driving on the left side of the road. Okay, we head around the bend. Cars going the other direction, and then one coming right at you. All right. So when we go ahead and take a look at how this process occurs, this is what the car ends up looking like, the van that you're in after the collision. They're going to show it again. It jumps the median and bam, right into the front hood. All right. Now, that is the definition of an unbalanced force. And this is not the only example we can use. What I would encourage you to go ahead and do is pause the video at this point and go do your Ed puzzle on Newton's first law in the NFL. This will talk about it a little bit more in a sports framework. I know we do this a lot, but it gives you an idea of how Newton's law works in action when people are interacting with other people. So go ahead, pause the video here, go watch the Ed puzzle, and then come back for the last little bit. Welcome back. I hope you enjoyed the video. Now we're going to go ahead and move on as we finish up to our last slide. And this is going to go ahead and take a look at what is the big misconception. What do people most often misunderstand about Newton's first law? Remember, Newton's first law of motion declares that a force is not needed to keep an object moving. Its natural tendency is to want to continue doing whatever it's been doing. So if it's moving, it wants to keep moving. If it's at rest, it wants to stay at rest, unless it interacts with an unbalanced force. Whether that unbalanced force is the car collision we talked about, or whether that unbalanced force is another defensive player trying to stop the offensive football player from making it to the end zone. Take a moment to go ahead and do a quick little physics test, if you will. Take a book, a large book is better, and then try and slide it across the table and watch it slow down and come to rest. The book in motion on the tabletop would not want to come to rest on its own, but it comes to rest not because of the absence of a force, but the presence of a force. And that force is friction that brings the book to a stop. So without the force of friction, the book will continue to move at the same speed in the same direction forever. Well, or in our instance, at least until it gets to the end of the tabletop, and then gravity, which is also applying a force, takes over. So remember, a force is not required to keep a book moving. A force is not required to keep a sled moving. A force is not required to keep any object horizontally moving in motion. The force will cause the motion to stop. This is the unbalanced force we've been talking about. And when we think about projectiles and vertical motion, you have to remember that a projectile, by definition, is impacted by the force of gravity, which automatically creates an unbalanced force. So we are no longer following the simplistic Newton's first law. All right. If you understand what the concept is here, it's actually pretty powerful, but it is definitely a misconception that many people have to overcome, that the natural tendency seems to stop. Well, that's what we see, but why is that occurring? Because forces are all around us, and then the force is what causes the stopping. The natural tendency is for it to not stop and continue doing what it's doing at the same rate it's doing it forever. All right. All right, guys. I hope you got something out of this. Take care of yourselves. Hope you're doing well. We'll talk to you soon. Take care. Bye bye.